Apply the alternating series test to sum n equals 1 to infinity n over negative 2 to the n minus 1. So what we have to do here is first of all identify our an. Our an is equal to n over 2 to the n minus 1. So we're kind of leaving out the negative part, which can be factored out, which is negative 1 to the n minus 1, and leaving us with a positive portion of the summand, which is n over 2 to the n minus 1, which is our an. Now, we need to show two properties for our an. We need to show that an satisfies 1. It is decreasing, so an plus 1 is less than or equal to an. And we also need to show 2, limit as n goes to infinity of an equals 0. And if both of these criteria are met, because this series is alternating, it converges. So let's go through and do this. For 1, we have an plus 1, which I guess is going to be n plus 1, divided by 2 to the n plus 1 minus 1, which is just 2 to the n. That we have to show is less than or equal to the general term an, n over 2 to the n minus 1. So let's use cross multiplication here, and we're going to get n plus 1 times 2 to the n minus 1 less than or equal to, and on the right side we're going to get n times 2 to the n. But I'm going to write that as 2 times 2 to the n minus 1. The reason why I'm writing 2 to the n this way is because now I'm going to be able to cancel the 2 to the n minus 1 from both sides. And if I subtract n, then I'm going to get 1 less than or equal to n, or n greater than or equal to 1. Since n is greater than or equal to 1, this condition being equivalent to this, proves number 1 is satisfied. All we have to do is look at 2. 2, we have the limit as n goes to infinity of n over 2 to the n minus 1. And this is going to be infinity over infinity, so this is going to be an indeterminate form. However, we can look at this as the limit as x goes to infinity of x over 2 to the x minus 1. Now, that's still going to be infinity over infinity, but the reason why we would do that is we can apply L'Hopital's rule to this. It would technically not make sense to apply L'Hopital's rule here, because this is just for integer values. So for example, this is 1 over 2 to the 0, and the next term is 2 over 2 to the 1. So this is a discontinuous function. This is a function only on the integers, and L'Hopital's rule applies to functions, of a real variable. So that's why it's technically correct to write this. Now, applying L'Hopital's rule here, we get the derivative of x, which is 1, and then the derivative of the power function 2 to the x minus 1. That is ln 2 times 2 to the x minus 1. Now, if we let x go to infinity here, the numerator it stays 1, but then the denominator is going to increase without bound. And so our limit is going to be equal to 0. And that does it. That proves it. Since the limit as n goes to infinity of an is 0, and since we have a decreasing summand for an by the alternating series test, our series from n equals 1 to infinity, n over negative 2 to the n minus 1 converges.